of supermassive black holes. En passant, I'll talk about the event horizon observations of M87 and Sagittarius I stars, which is the black hole of the Milky Ways, call it Sagittarius A star. And then I'm going to talk also of my work on feedback of supermassive black holes. And finally, a little bit of our project. We have an approved project to observe supermassive black holes in active galaxies with the James Webb Space Telescope. Okay, so just for completeness, let's remind ourselves what is a black hole. So black hole is just a consequence of gravity. So if you have this old Newton equation with the force, gravitational force, if you increase the mass of an object, you increase its gravity, but you also increase the gravity if you decrease the radius. So what will happen if you keep increasing the mass and decreasing the radius, where it will go to the limit, which is the black hole, where in a black hole, the escape velocity is the velocity of light, so not even light can escape from this imaginary surface, which is the surface with the Schwarzschild radius. Okay? And this, this guess of the presence of black holes or black stars was made already back in the 1700s by John Michell and Laplace. In the Einsteinian view of gravity, so the masses in the universe warp the space-time around it, and then you have any object that enters the gravitational field of a black hole will follow a curved path, but not only objects, not only bodies, but also the light radiation will follow a curved path due to the warping of the space-time. So we have the space-time curvature given by the Einstein field equations. So the stress and energy tensor will dictate how the space-time curves. Okay, so we have objects with different gravity, and the sun, for example, distorts a little bit the fabric of space-time. If you have a white dwarf that has the mass of the sun, but the radius, much smaller radius, you have a deeper warp, and then you have a neutron star, even deeper warp. And then the limit is, when you have a black hole with infinite curvature, and then you have a singularity, all the mass is in the singularity inside the black hole. One property of the black holes that we use always is the radius of the event horizon that was derived by Karl Schwarzschild, solving the Einstein equations, and this is the radius from where nothing can escape, not even light. Okay, so we see that the radius is only proportional to the mass. So, and for example, for the Earth to become a black hole, we have to compress it to 9 millimeter radius. Okay, the Sun to 3 kilometers, and the Sun has 700,000 kilometers of radius. In the Milky Way, we have a supermassive black hole in the center that has 4 million solar masses, and then it is, Schwarzschild radius is 12 million kilometers. Kilometers, not kiloparsec, okay. Well, a little bit of perspective now. So we live in a galaxy, the Milky Way. This is an actual image of the Milky Way in the sky, but we are inside it, so we see it from inside. This is the center of the Milky Way. So we are 27,000 light years from the center. And the Milky Way is a spiral galaxy that has a bulge and a disk with spiral arms. And we see the universe and the galaxy from inside. Two important structures that, of galaxies are the bulge. This is Andromeda galaxy, and only 2 million light years away. And another thing that is important to remember is that the universe is so big that and the velocity of the light is finite. So we look at Milky Way as it was 2 million years ago. M87 is another type of galaxy, an elliptical galaxy, which is 53 million light years away, and it's has only bulge. Okay, so Andromeda has bulge and disk. M87 only bulge. Well, so when we extrapolate observing the universe farther and farther away, we can observe the whole history of the universe. So this is, maybe you know already this, this figure from WMAP that shows that we are in a universe with 13.7 billion years, and when we look far, we are looking to the past of the universe, and we are reaching now, we have reached already we can see the microwave background radiation. And with James Webb Space Telescope, we are aiming to see when the dark ages finish, when the first stars in the first galaxies form, okay? So we know that's more or less in a few 100 million years, but maybe we can go down to 50 million years with JWST. So this is one of the main goals of the JWST, to find the end of the dark ages. Okay. We have, this is the Hubble Ultra Deep Field that maybe you already have seen. So from the Hubble Ultra Deep Field, we know now that the universe has more than 20 billion galaxies in the visible universe. Okay? At least in the universe that we see, there are at least 20 billion galaxies. And in each one of them, there is a supermassive black hole in the center. Okay? So we know that all galaxies that have a bulge, actually there is a requirement. The galaxy has to have a bulge. When the galaxy has a bulge, it has a supermassive black hole. Okay? So just quickly, I will not enter into detail here, but this is like a supermassive black hole simulation with an accretion disk, and you have all the gravitational effect of gravitational lensing, showing the accretion disk around it, and the back part of the accretion disk, the top part of the back, making this part of the ring, and the under of the accretion disk, the bottom part of this ring. Okay? And besides, each galaxy with a bulge has a supermassive black hole in the center. They have an estimated 100 million stellar black holes in the galaxy. Okay? This is the end result of the evolution of massive stars that explode as supernovae, and then you have a black hole resulting from this explosion. And these stellar black holes are usually more easily found in binary systems, when it has a bright companion and it captures mass from this companion in the accretion disk. Okay? One important property that we know already from Hubble observations is that the mass of the supermassive black hole inside in the nucleus of galaxies is proportional to the mass of the bulge. So bigger bulges have bigger black holes. And we also know that, so besides being ubiquitous in bulges, a I just showed that its mass is proportional to the mass of the bulge. But then we have also, we know already from studies of the distant universe, that the mass accretion rate density, which is this red line, follows the star formation rate density over the history of the universe. So they seem to evolve together, the supermassive black hole and the host galaxies. And they evolve together, and also there is, I would like to show you that the black hole, supermassive black hole, produces feedback that in the form of radiation and jets from the accretion disk that affects the galaxy where it is inside, okay? But how to observe these black holes, okay? I have observed mostly, and most observations are via electromagnetic radiation, but one can ask how you can observe black holes with electromagnetic radiation if they don't emit light. So actually, we observe objects that radiate, that send the electromagnetic radiation, that orbit the black hole. Okay? And also via the same process that José was talking before, gravitational lensing. And there are some results of black holes passing in front of stars, and we see the effect, the variation caused by the gravitational lensing, amplifying the light of stars when it passes in front of it. Okay? And also, you already know also that since 2015, we began to detect gravitational waves from mergers of black holes or neutron stars with black holes, and with these detectors LIGO, Virgo, and CAGRA. In the future, we hope to detect not only stellar, because we have detected only stellar black holes now, the merge of only stellar black holes, with these gravitational wave detectors. In the future, we have this project of the LISA, which is an interferometer similar to LIGO, but that will go into space. Okay. To talk about my work, I would like to begin talking about quasars. Okay? So quasars can be considered one of the first evidences of the existence of supermassive black hole. So quasars can be considered the most luminous objects in the universe, and they were discovered as radio sources. When the distances of them were discovered, it was found that the luminosities were almost 1,000 times, could reach 1,000 times the luminosity of the Milky Way, the whole galaxy. Okay? And then, since the Hubble went to space, we now see that quasars are actually the center of galaxies. So quasars are not another entity, but it is in the center of galaxy. Okay. But how we can explain that in the center of a galaxy you have such high luminosity that can outshine by 1,000 times the light of the galaxy? So the explanation is that in quasars we have a supermassive black hole capturing mass. Okay? So this is an artistic conception, but the capture mass, because of angular momentum conservation, forms an accretion disk around the black hole. And then the released gravitational energy is used to heat this gas that is in orbit of the black hole, generates radiation, the disk emits radiation, sometimes winds, and jets. And so all this gravitational energy is transformed into this energy emitted by the accretion disk around the black hole. And the efficiency, when we calculate the efficiency of energy generation from the capture of mass to a black hole is very high efficiency. So we can show that it's 10% efficiency. Every bit of mass that is captured by a black hole, 10% of the rest mass is transformed into energy, radiative, jets, or winds. And this 10% is a very high efficiency that is much larger than the nuclear energy generation that we know that happen in the center of stars. And we now are trying to control the nuclear reactions to get energy, right? So the efficiency is only 0.7% of energy generation by nuclear reactions. So the accretion of matter to a black hole is much more efficient to generate energy. And then can account for the quasar luminosities, and we can say then that the black hole plus the accretion disk is the most efficient energy generator of the universe.
That is not in gravitational waves, right? Because gravitational waves can do better than that.
Can do better than that? Okay.
Yeah, they can go up to 29%.
Oh, 29. Yeah, okay. Okay.
If light, yeah.
Okay. Okay, so this is new. Okay. So, but the gravitational, okay, generator of, but what kind of energy we can generate with gravitational waves? The amount of energy. Okay, but I mean, if you want if you have a black hole and you send mass, it captures, it will generate energy in the form of radiation and winds, things that we can maybe use to.
Well, the hours we use to move mirrors in an interferometer.
Okay. Okay.
29% is a lot. Which system can emit 29%, can convert 29%?
If you tap on the angle wall, like Planck's knife, it's taking it out of Planck's knife would take it. Well, what if you can do highly spinning black holes merge? Okay, you can go all the way. But so far we've gone up to 5%.
Yeah.
Mm-hmm.
But that's higher than
the vanilla system is even less than 10%. The 29 is really a specific system.
Okay, so good to know. Okay, so my work is with active galactic nuclei, which are similar to quasars. Well, I work also with quasars, but quasars are a part of what we call active galactic nuclei, where you have matter being accreted by a supermassive black hole. In the present-day universe, when you look near the present-day universe, a few million, 100 million light years away, we see that 90% of the galaxies, in 90%, most of the galaxies, the black hole is quiet, is doing nothing, it's just there. But in 10%, the black hole gets activated and you have an active galactic nucleus. So this means that matter is being captured by the black hole and is producing radiation, producing jets, or winds from the accretion disk. So what I study in this AGN is how the supermassive black hole gets activated, how the mass reaches the black hole, and also the feedback processes of AGN. So which is the effect of the radiation, jets, and winds in the host galaxy. Okay. And nowadays, what we call the supermassive black hole feedback is very important because this radiation and these jets can hit the gas in the nuclear region and even farther out in the galaxy, can push the gas out, and then what happens is that these gas that are in the galaxy would be forming new stars. So if the black hole pushes it out or hits, then you have a delay in the formation of stars or even a halt in the formation of stars. Okay? And now galaxy evolution models need to consider the feedback of the black holes. Otherwise, they cannot explain the size of the galaxies that we see in the universe. And this is more or less what this cartoon here shows, that the luminosity function of galaxy with the galaxy luminosity. So for the black holes, what matters is this end of the luminosity function. So the observations show this distribution in the luminosity of the galaxies. And the theory without AGN feedback produces more galaxies. The theory of formation and evolution of galaxy predicts much more luminous galaxies than there is in the universe. So the models of galaxy evolution need to consider the feedback of the AGN to lower this number, so the galaxies don't get so many galaxies so luminous as the models predict. Okay? Então, so I would dare to say that if it was not for our supermassive black hole Sagittarius A Estrela, maybe the galaxy would be different. Maybe it would be much larger than it is. And maybe the conditions to form the Earth and life in Earth would not be present. So this would be our connection with the supermassive black hole. So we now see that the supermassive black hole have to be considered when you consider a galaxy evolution. Okay?
There's no feedback from our black hole, right?
No.
It was recently some feedback, because this new eRosita image, I don't know if you heard this. eRosita is this satellite X-ray that made an image, and it shows the Fermi bubbles. Have you heard about the Fermi bubbles? So it's a few million years ago, there was some outflow of energetic particles from the center of the galaxy that was seen in the Fermi in gamma rays. So now eRosita, that is in the X-rays, saw also this structure above and below the galactic plane. So it was active a few million years ago.
It was jets from black hole?
Yeah, so two lobes, energetic lobes from the black hole. So it's something periodic, the nuclear activity. So you have not periodic, but recurrent. So when you have matter falling into the black hole, then you have a cycle of activity.
But there's no accretion this?
No. We have a very low accretion rate. So they say that it is a toroidal structure. It's more like a hot ion torus that is surrounding the black hole of the Milky Way, more than a thin accretion disk that you form when you have a very strong or a high mass accretion rate. Depends on the quantity of mass being accreted per time.
So this was seen, this toroidal?
No, it was seen just the lobes, the jets, the outflows, yeah.
So, all the bubbles exist in the galaxy. I mean, apparently the sun is inside another bubble.
Another bubble, okay.
And that is probably a small black hole, something else.
Okay.
But the question is, how many black holes like that, exist in the galaxy history? Have you an idea?
You mean a black hole like the Milky Way?
Like this one that the sun is inside, because probably not too big.
Yeah, I'm not very familiar with it, but for example, I know the statistics of stellar black holes, that is about 100 million for a Milky Way. So we have black holes, stellar black holes in systems, or maybe floating around in a large number, 100 million, okay. Okay, so this is one example of an active galaxy, one of the closest, actually is the closest to us, only 12 million light years away, which is Centaurus A. So we can see this is it's an elliptical galaxy that is capturing a spiral galaxy, and this material from the spiral galaxy is feeding the black hole inside Centaurus A that is emitting these jets. So this is a very large region tens of thousands of light years, even 100. And you have this bubble similar to the Milky Way, this bubble here in X-ray. It's not so different from the one in the Milky Way. And there is this jets in Centaurus A. This is an active galaxy that is producing all this activity. So showing off a bit with the observatories that I used to go. I don't go anymore because you have the space observatories. We do remote observations, but it was a lot of fun to go to the observatories back in the day. So these are the SOAR that is 30% Brazilian. This is Blanco that's not Brazilian, but I think Rogério uses this Blanco telescope for DESI. Right? And this is the Gemini, and you can see the comparison. It's a 4-meter mirror. He's 8-meter mirror, so I'm here in the bottom. But now we are going to the giant ones. So I have done a lot of work with this technique, Gemini, which is integral field spectroscopy, where you observe a galaxy, both imaging and spectroscopy of each position of the galaxy. So it's a very powerful instrument, and you have also at the James Webb, all major observatories now have these instruments because they are very powerful. You can image a galaxy or whatever nebula in different wavelengths. So, and you can have kinematics. It's a lot of information you get. And also, we can use ALMA. We have a project with a PhD student to observe some quasars with ALMA that got approved. And we got the Hubble. Oh, sorry. And the Hubble and Chandra. All these observatories we use. One example of a study that has some repercussion was this black hole inside one galaxy that NGC 1097, that is 15 million years away. And I was observing the kinematics of the central region of the galaxy, and inside this ring, it's a ring of star formation. This is the ring. And then I was observing with the technique of long slit, several position here. And then in the nucleus, I saw the signature of a non-resolved, it was not resolved, it's just a point, disk that is similar to an accretion disk, but it's a little bit larger. And so actually is what we call the broadline region surrounding the accretion disk. So I could see this object from the spectra of the region. So this is the spectrum. I don't know if you know what is a spectrum. So when you observe and spread the wavelengths of the light, this is a region that we call the H-alpha line, which has rest wavelength 6563. And usually we see these narrow lines. All these things very narrow. This is emission from gas. What I saw in the nucleus of this galaxy was something very strange, which is this double peak structure. It's a very broad line with a double peak structure. And this means you can model this via a ring of clouds surround the black hole with velocities that reach up to 10,000 kilometers per second. Okay? So this is, we have followed this. And so, and we can see the variation of the clouds. So this is a simple model where this disk is actually made of several clouds. And then we could reproduce what we saw in the spectra. So we did this monitoring for many years until almost the disk seems to have disappeared, this disk of clouds. But so this is something that one can do. And I'm following the behavior of these broad lines that you see in AGN, active galactic nuclei. And now I'm participating of a project being done at the Hubble Space Telescope, just finished to observe all this structure. This is a summary of the nuclear structure, but it's very similar to what I showed. We are looking for these clouds. So this is the black hole, and this is the disk, and these are the clouds that answer to variations here in the inner part of the disk. So we study the variation of the nucleus, and we study the variation of the clouds. We do reverberation mapping to understand the structure of the disk and even calculate the mass of the black hole. So this is a very powerful technique, but it's very time-consuming. It's 1 year of observations with the Hubble Space Telescope, obtaining spectra every week or sometimes twice a week. So this project finished the last year, and the papers are coming out. Regarding the feeding of black holes, in 2009, I wrote, together with a former student, this review where I put together all our observations, also observation of others, of how you can feed that supermassive black hole, how you can make the supermassive black hole alive. So what we concluded is that at large sizes, 10 kiloparsecs, if you want in light years, you have to multiply by 3.26. 10 kiloparsec scales, more than 10 kiloparsec scales, which is extragalactic scales. We have galaxy interactions. We see a relation between galaxy interactions and the presence of an AGN. So galaxy interaction seems to be a means to send gas inwards to activate the black hole and make an AGN. And then you have intermediate scale, galaxy scale structures, bars and spiral arms. We did a lot of work also in 100 parsec scales, where we found these structures are in the nucleus. We call nuclear spirals, nuclear disks. And we could do kinematics of this and see that there is some inflow happening associated with these spirals. Okay? So this was most of the work we have done. And here is the structure of the AGN. And this work that I just mentioned is to study the broadline region, which is just outside the accretion disk. This is an example of how we work with the integral field spectroscopy. Remember that I mentioned that integral field spectroscopy is a technique that we are using to map the feeding and also the feedback of a supermassive black hole. So here is 3 spectra in different locations over the image of the central 100 parsecs. So what we did was use near infrared. So this is a molecular gas line, H2. And these are some absorption from stars. And this is the bracket gamma line, calcium line. So we use these lines and get the kinematics. For example, we get the kinematics of the molecular gas from this line, and we get the kinematic of the stars from these CO bands. And then we look for inflows as the residual between gas motions in this line and regular orbital motion in the galaxy potential. So just to illustrate how we look for the feeding, for example. So here, this is a very small region, 450 parsecs, not so small, but 100 parsec scales. And so from the CO bands, we get the velocities of the stars. So this means that the stars in this side of the field are coming towards Earth. This means the stars are going away from us. So this is velocity in kilometers per second. And then we could fit a model, a rotation model for the star. But when you look at the gas, molecular hydrogen, you see something different. So you see this like a spiral pattern on top of this rotation. So there is some contribution from rotation, but there's something else. When we do this analysis, subtracting the rotation component, we see that in the far side, we can work also which is the far side of the galaxy and the near side of the galaxy. So the far side, we see a lot of blue shifts, means gas coming towards the center. In the near side, gas going away. And then we see some inflows in these scales, but here in the center, we see the opposite, and then we conclude that there is an outflow also. So what happens in the AGN, you always have some outflow, and to see the inflows is hard. But in the low luminosity AGN, you can see the inflows. And this is what an example of what we have done. Okay. The center, very center, I have to tell about, the first images of the event horizon of a black hole, right? So this is the Event Horizon Telescope, a bunch of observatories observing together in the same source. They observed M87 and also Sagittarius I star. And to observe this event horizon of these black holes, it's equivalent to observe an orange in the surface of the moon. So it's a very challenging observation, okay? So they needed all this. And so when you have this resolution, they could, from the light coming from the vicinity of the passing through the vicinity of the black hole, you form this halo of light deflected by the black hole. So you could build these two images, right? So this is the Milky Way one, and this is the M87 one. They look similar, but M87 is 1,800 more distant, but it's 1,500 times more massive. So in the end, you have a similar size image. But M87, for example, the size of this event horizon, the event horizon is actually inside. It's larger than Pluto's orbit, while Sagittarius I Estrela, which is the black hole in the Milky Way, is smaller than Mercury's orbit. So it's very different to black holes. So I'll pass quickly. This is just to mention that the Nobel Prize on black holes. To talk, the final thing I want to talk is our work on feedback. So I mentioned to you that feedback is considered now in the models as important for explaining the galaxies, the evolution of galaxies. And so we did some works with also observing with the integral field spectroscopy. This is one radio galaxy. So you have radio jets, you have hot gas, and we have mapped the outflows in the optical and ionized gas. We found an outflow from the vicinity of the black hole of 25 solar masses per year and a power of 6% of the luminosity of the AGN, which is very strong, and this has impact in the galaxy. But on the other hand, we observed a sample of quasars. This is some quasars at 3 to 4 billion light years away. And we have the stars and you have the gas. So the gas is showing the feedback of the black hole extending to large distances. And so these are some work that we have done trying to calculate the power of the outflow and comparing it to previous measurements. So this is the mass outflow rate as a function of the AGN luminosity. Power of the outflow is a function of the AGN luminosity. Our samples are these stars. And then what we find is that it's a little bit below the 5% that we found for that radio galaxy that I mentioned. So it's still a little bit lower than we expect to have an impact on the evolution of the galaxy. And we are now looking at higher redshift in the more distant universe, where in the epoch we call cosmic noon, when the universe was more active. So maybe the power of the outflow was stronger then. And also in other gas phases, in molecular and neutral gas, that we are using ALMA for this. And to finalize, just mention some works that we are joining, or, well, the manga, we just finished some work. We are writing a couple of papers still, which is the Sloan Digital Sky Survey, which is a big size IFU in terms of covering the whole galaxy. And also, we are members of LINEA, and we are beginning now to prepare for the observation, the first observations with the LSST, the Vera Rubin telescope. And I also have some projects with the PFS, Prime Fox Spectrograph at Subaru. And we have this project that was accepted. The PI was Rogemar Riffel and Marina Bianchini, but I'm a collaborator, to observe the James Webb, which is blowing star formation wave, unraveling molecular winds in AGN. Also is to observe the feedback from winds from AGN in the molecular gas that is observed in the mid-infrared with the James Webb Space Telescope. And this is just one other object. It's not our object. This is Stefan Quintet's, and the top galaxy of the Stefan Quintet is an active galaxy, and we are planning to do something similar. This is the IFU in the mid-infrared, and you see blue shifts and red shifts, and so this is probably an outflow. So we are planning to do something similar, and this first observation showed this is possible. Finally, the big telescopes that we are hope to use in the future, and thank you. Some water.
Hi, thanks for the talk. I have two questions. One of them is quite naive. If you could go back to that image where you had the elliptical galaxy.
Okay.
I wonder if at that scale, what we are looking at, the other dots in the image that we are looking at, if they are actually either galaxies, stars, or a mix of both.
Which elliptical galaxy?
It's further back. It's a.
Yeah, when I mentioned
yeah,
it.
that one.
Oh, okay. This.
No, the next one.
The next one. Okay.
No.
No. Okay, I passed. Okay.
That one,
okay.
Yes.
This is Centaurus A. It's an elliptical galaxy that is merging with a spiral one.
All right. So, but the other dots in the image, they are stars. In this scale, we are looking at other stars or other galaxies.
No, this is mostly stars from our Milky Way.
Oh,
okay. This is it's a bit low latitude, low galactic latitude, so you see a lot of stars in the field.
Okay. And the second question is, you're probably aware of the Penrose process, the Penrose mechanism of energy extraction.
Okay.
And I would like to ask you, as an expert in this field, like, what is the actual relevance of the Penrose mechanism in this astrophysical scenario, right? Is some variant of the Penrose process taking place? Is something similar taking place? Or is it possible that the Penrose mechanism, as it was described originally, is taking place in this case?
Yeah, I'm not familiar with the Penrose mechanism, so if somebody here
maybe I can respond.
Okay.
So prior to the Penrose mechanism you refer to, in the very same paper, there is another Penrose mechanism, which is just the extraction of energy from a rotating black hole.
Yes.
And the models that underpin these jets, actually, well, one of the leading models uses explicitly that method, that Penrose, that process.
Okay.
So it is very much in the foundations of the model.
Oh, okay. Yeah.
So there's an extraction of energy from a rotating black hole. So yeah, I was familiar with the name, but I know of this process.
The name
so
would be
to produce jets,
Yes.
it's considered to be important. You can extract energy from this from this mechanism to produce the jet.
Yeah, I think because the Penrose process, I think it's often considered to be something more academic, like it you have, because you need to have a particle to break up exactly in a very particular way and interact with the black hole in a very particular way to extract energy. And so I was wondering if, like, statistically, you have a bunch of particles, a bunch of gas around the black hole, right? Statistically, one might break up just to the exact same, the exact way that it needs to break up to produce energy. But okay, thank you. These were the questions.
Okay. So hydrodynamical simulations are very important in order to find out the process of large-scale structure in the universe, as Jessie pointed out in her talk yesterday. And this is one of the main uncertainties in extracting cosmological parameters from observations like the dark energy survey. So the question is, in these hydrodynamical simulations, there are many parameters, and some of them are related to feedback processes. And the question is whether your observations instruct or help to bracket these parameters for these hydrodynamical simulations.
Yes. Yeah, it's one. It's one of the goals of our project is to look for, how big and how effective is the feedback, right? So when we look in the nearby galaxies, I began working with the nearby galaxies, and I ended up finding a lot of inflows and a little bit of outflows. So you need a lot of activity, so large accretion rate to produce enough feedback. Even so, the first sample of quasars that we have worked with are not that powerful. So we are a factor of 5 down. On the other hand, what happens is that we are doing like kinematic studies of the ionized gas. So you have the molecular gas, you have the neutral gas, and you have also the radiation that produces pressure in the medium. And one interesting result that we got from the Manga observation is that with GMOS, we are looking the inner 1 kiloparsec, 2 kiloparsec, 3 kiloparsecs, okay? In the nearby galaxies with Manga, we covered the whole galaxy. And we could find out that with a sample of AGN and a control sample, that the AGNs always have the lines a little bit more broadened compared to non-AGN out to very large distance from the nucleus. So there is some feedback in the form of radiation and heating of the medium, agitation of the medium, that is very subtle. With GMOS, we didn't realize that because we are looking for the big feedback. But with Manga, you could see that the effect is spread all over the galaxy. So it is present. And so, but the quantity is still, it's a bit uncertain. And the models always push to higher numbers. When you see the simulations, they plot these explosions from the black holes and, hitting large. Yeah, it's more than supernova has to be, yeah. And so in the simulation, you see all this, and I'm trying to see in the data, and I don't see those spectacular things. But when I talk with people from theory, they said, no, but this is it's energy. So it's not only ionized gas, it can include neutral gas, it can include molecular gas, and there is the radiation that induces some pressure, and sometimes it's not so easy to measure.
Can I ask a follow-up question? These simulations, how do they account for the presence of the black hole? This is just a Paczynski Vita or something that is approximate that might miss a very important component contribution from the physics itself?
I'm sorry, when you have these expressions.
Yeah, so are the simulations using general relativity?
Oh,
or are they just representing it with a point Newtonian potential that has been slightly modified to capture in very hand-wave ways the role of a black hole?
Yeah, I think it depends on the simulation, but when you do a large-scale one, maybe the relativity is not so well sample, you know, to the detail of the masses.
I have a question. If, I will. So I'm intrigued by this correlation that you mentioned between AGN activity and star formation.
Oh, okay.
So, but I don't understand which way it goes. I mean, then the AGN activity basically blows away gas from and rip off the gas from the stars?
So, this correlation is just an observation. So, when you count the nuclear activity and you calculate the mass accretion rate, and then you plot as a function of redshift, and, you know, to see the evolution, it's parallel, goes parallel with the star formation rate. And so they evolve together. So one thing, but one is off by 3,300, or so, 3,300 times. The accretion rate is lower than the star formation rate. Okay, so one can understand this via two mechanisms. One is that the same gas that is forming stars, the residual or something, is going to feed the black hole. So they grow together when the galaxy formed and the galaxy evolved. The stars are forming and the black hole is being fed. Okay, so the black hole is growing in consonance with the galaxy. But there is also this feedback. You feedback, and the feedback is you have a cloud of gas, and it needs to cool to form stars. If you have some feedback, radiation outflow, it will disrupt the cloud and won't allow the formation of stars, or at least will delay the formation. And what happens is that it looks like you have a delay between the formation of the stars, because we see some correlation also between the formation of stars and the black hole. But it seems to be a delay because the stars form and then they evolve, they lose mass, and then the black hole seems to be more active. So we do these studies of the stellar population ages together in AGN, and we are concluding that the stars are not really young, they are a little bit older. So it looks like there is a delay between the star formation and the feeding of the black hole.
No, I was thinking because there is a curious feature that the black holes that LIGO has seen, they are in the region of 40-50 solar masses. And the black holes that we see in our galaxy through electromagnetic observation, they are lighter, up to 20.
Yeah.
So that might be related to the fact that our supermassive black hole is not active, so stars are not being accreting so much, so basically our galaxy is going to...
You mean from the gravitational wave, from the gravitational waves?
Yeah, we see all the gravitational waves we see, they point to more massive black holes than the one we see in our galaxy.
I don't think that maybe this is a bias of, you know, what the instrument is tuned to observe.
We could see 20 solar mass. I mean,
really?
There's not much bias for a lower mass black hole. I mean, you lose a little bit of reach, but not that much. So it's really pointing to the fact, I mean, it's preliminary. It seems that our galaxy are kind of lighter black holes. Unless you tell me that the black holes we see electromagnetically are more likely to be lighter than more massive, but that's not true, right? I mean, electromagnetically we could see 50 solar mass black holes, right? Could we?
50
solar mass black holes, there's no point. There's no
the
problem.
point is that to build a black hole that is, you know, 50 or something, you have to have very, very massive stars, because the black hole is the remain of a star that exploded. So, and you know, most of the mass of the star goes away, and you have, so I wonder, we don't see so massive stars in the Milky Way, and even, you know, Magellanic Cloud, well, where we can resolve stars, M31, Andromeda. So it's an interesting question, because usually these events detected by LIGO, they are very massive and kind of far away, right?
Sure,
it's like a few billion light years.
Yeah, or 100 of megaparsecs. 100 of megaparsecs, so at least hundreds of thousand light years.
Yeah.
Billion light years.
But no, it has to be a few billion to have some evolution. I don't know. But yeah, it's a puzzle. Yeah, I didn't read too much about
So
to see how people explain. But I agree that in our galaxy we see, you know, the stellar mass black holes are not that big. Yeah.
Maybe it's in a handle to relate binary black holes, massive solar mass binary black hole to AGN. Maybe.
You think? Yeah.
Okay. I'm pushing it too far.
Okay. Yeah.
Going once, going twice. So if there are no further questions, before we thank Thaisa, I remind you, come down to sign the dinner paper and then stay here outside for the group picture. And now we can thank Thaisa, please.
Thank you.